All right. Today is officially your last day of new information in calculus, despite the fact that some of our review that we will do might feel new because it's been so long, but this is it. We have saved the last little part here, very similar to what we did yesterday. We are taking some sort of shaded region, some area, we're revolving it around some axis. But today, either the axis or the fact that we have two functions in our picture changes our shape just a little bit as we revolve it around an axis. So for example, if we were to look at two functions bounding a curve like this, and I told you to revolve that around the x-axis, seems very similar. But if we were to look at a 3D picture, once I revolve that around my x-axis, what happens is we end up with an opening in the middle, okay? Because as I revolve that, there still will be nothing here. And so we get a gap between our solid and our axis of revolution, meaning that as I slice it and get a disc, my disc has a hole in the middle, okay, which they refer to as a washer, or some people call it a donut. Okay, so we do have to alter a little bit. Now back in geometry, I am sure this is like one of the most standard questions as you're finding area of solid or area of your shapes. And that is just the idea of taking the whole circle, finding its area, and then subtracting out the little unshaded part in the middle is ultimately what we are going to be doing. So the area of our washer will come from looking at these two, and I will always note them, I think, the same way your book does, where the outer edge, pretending like the whole thing would be filled in, we will call big R for our outer radius. And then our inner circle, we'll refer to that one as little r, just to distinguish between the two. Now we could draw out each of those separately, but they both have a pi in them, right? They're circles, pi r squared and pi r squared. And so what you'll see me do a lot of times is just factor that pi out since they both have a pi. And it'll be pi times our outer radius squared. There's your first circle, pi r squared, minus the inner radius squared. Pi little r squared would be the area of that smaller circle. And then our volume is just putting that into our integral. And again, the direction that we are stacking these up does not change from what we've been doing. Whatever this will fill in, matching whichever direction we are stacking these washers today. Now, finding that radius, again, we have to consider our radius is always going to be the distance between our curve and our axis. And depending on which one is the top and the bottom of those two options, that's how we would identify our radius of that circle from our curve to our axis. So let's look at some examples that have washer shapes as we revolve them. So it says the region in the first quadrant enclosed by the y-axis and the graphs of y equals cosine of x and y equals sine of x, which would be, if we remember what those look like, here's our y equals cosine of x. Actually, I'm going to write it up here. And that's your y equals sine of x. And the y-axis means that our shaded region will be here. So it's this area right here that we are going to revolve around the x-axis. Very similarly to how I would do this for the disk method like yesterday's, I would consider what it looks like once I reflect it, because that would be the top and the bottom of our solid. So if I were to reflect this over that line that we are revolving around, we would have our sine curve again here. Our cosine curve would be extend this a little bit here, coming this direction, and there's our reflected solid. And so this time when we go to draw that circle around our axis of revolution, connecting our top function to our bottom function, I'm actually going to end up drawing two of them. So our outer function goes from cosine down to that reflected cosine. And then I'm going to draw the inside of that washer because there's a hole here connecting those functions. Okay. Questions so far? So our radius is going to go from our axis. There's our smaller radius. Bigger radius is going to go all the way up to that top function. So instead of looking at a singular disk, we'll look at a singular washer with that hole in the middle. Our radius again goes from our axis up to our functions. Outer radius, so considering that longer one, top minus bottom, well, our bottom is going to be our axis at 0. So it's just our top function there. And our top function is cosine of x. The smaller radius is here. Again, top minus bottom. Well, again, bottom is just your axis of 0. So our top function there, or top of that radius, would just be sine of x. Good so far? Okay. And as always, then just taking a moment to identify the area of one washer. Pi outer radius, capital R squared, minus inner radius, little r squared. And then same thing with our volume. These washers are stacking up along our x-axis because that's what we are rotating around, which means they're stacking from left to right. They did not tell us where it stops. We need to figure out our point of intersection, and that is where our cosine curve intersects our sine curve. Now, assuming we get a calculator, you can go graph sine and cosine and get that number from your calculator. But if you also think unit circle, where on your unit circle is the cosine equal to the sine? Pi over 4, right? They have the same value at pi over 4. So we would be looking from 0 to pi over 4. You don't need to remember that second number, but it's the square root of 2 over 2, right? That's what their value is at pi over 4. But because we're integrating from left to right, we're integrating with respect to x. I really need the x values, which would be 0 out to pi over 4 to set up my integral for the volume. From 0 to pi over 4 of our area. Okay, grab your calculators, because remembering how to type in correctly cosine squared and sine squared all into an integral is a little bit tricky. So let's go ahead and take a second and make sure that we can do that. All my physics people, make sure you are flipped back to radian mode. And if you're having trouble getting it typed in, let me know. And it looks like we might be getting an answer of pi over 2. You guys agree? Good. All right. If you got it as a decimal equivalent, you'd be looking at what's like 1.5, yeah, which is the same thing as pi over 2. Any questions? All right. So what I put in here is just looking at washer methods still, but are other options that we need to look at, which is revolving around something like our y-axis and then something that is not an x or y-axis. Okay, so that's the rest of our examples today. Same idea, just different directions. Find the volume of the solid that results when the region enclosed by the curves is revolved around the given axis, and this time our curve is y equals the square root of x, y equals x squared, and we are revolving it around the y-axis this time. So as always, my suggestion is just start by drawing yourself a picture to visualize what your region looks like and what that means for what it's going to look like as we revolve. Okay, as we are doing this, our square root of x looks something like that. Our x squared, a different color here so we can distinguish the two, would look something like that. And we are revolving around our y-axis this time. So first of all, if they say that we're revolving around our y-axis, okay, what does that kind of tell you about what we need to do with our equations? I would say actually this conversation right here is probably one of the biggest mistakes that we'll make, is that we get too far into the problem before realizing that we needed to do this and have to go back and do a lot of work, because there seems to be nothing wrong with what we have so far, right? But if I am revolving around the y-axis, think about that. I'm reflecting this over my y-axis, right? So my reflected picture is going to look like this, that the circles connect, and my circle that I draw for this needs to circle my y-axis, my revolution, axis of revolution here. So out to my outer function, and then the inner part of that washer is going to be opened up right here. But we are going to integrate with respect to what? Y. My washers are stacking up bottom to top, okay? And the thing that we forget as we get into this is it'd be really easy for me to go over to my area for my washer and talk about that my radius is going to be the square root of x minus the, the x squared minus the square root of x, right? But I actually need these in terms of y if we're going to integrate with respect to y, okay? So actually the first thing I would do is solve each of these. For x. That's probably the thing that we forget, and we get all this work done and then have to go back and change all those equations. So just think about what you're integrating with respect to. Here we do actually get plus and minus the square root of y, but that is just going to be the positive version of it is over here. So this is your positive square root of y, and this is your negative square root of y, and I'm really just looking at this side here to get my radius. I just need a radius one direction, but it really is plus or minus, right? Okay, so now I can go look at a washer now that I have those written in terms of y. And think about what my inner and outer radius is. We are going to an axis, so we don't have to worry about that part of it. But my outer radius is going to go to this green function, which was the square root of x. Which was x squared. Solve for y is now, solve for x is now the square root of y. So that green function being my outer one, when we solved x squared for x, we get square root of y. So my bigger radius is the square root of y. My inner radius goes to the pink function here. And when we solve, that was originally y equals the square root of x. When we solve that, we get x equals y squared. Again, going to our axis, so there's not like a right and left function there. Therefore, our area is pi times our outer bigger radius squared minus our smaller radius squared, or Clean that up a bit. Y minus y to the fourth. One of the things we haven't spent a lot of time talking about, but today you're going to have to focus a little bit more on, is looking at our intersection points for the bounds of integration, because now we're looking a lot more at two functions like we did on the last page. So again, thinking about what is the intersection of these two functions, you really can go back to what you're more comfortable with. If I want to look at substitution and my point of intersection here being the square root of x equaling x squared. Okay, so use your algebra skills to solve this. One of the things I'd probably do is square both sides here. Get everything onto the same side. And we find out that x equals 0, or x cubed minus 1 equals 0. So there would be our 2 points of intersection in terms of x. That's the x value here. If I plug that back into any function, x squared or square root, we get 1, 1. Or I go to my calculator if it happened to have been a calculator question, and it can just tell me that, right? Use your calculator function for point of intersection. What do I care about here? We are integrating with respect to y. So we are going bottom to top of that shaded region, and the bottom would be on our y-axis 0. The top is your y value of that point of intersection, which is up at 1. And as we go to our calculators, I know you guys know this already. Still type in x, or yeah, still type in x, even though we are going to write down with respect to y. Okay, questions you have for me so far? I'm seeing 0.942. Pi over 2. 0.942 is what I saw down this row. Any questions for me? Okay. Changing our axis now to something that is not the x or y axis. So this time we are going to revolve around y equals -1. So again, draw a picture for yourself, because instantly it doesn't look like, it looks like I might need to change these two in terms of y, like solving, because I think about like revolving around the y-axis, but the line y equals -1 is actually a horizontal line, right? Similar to revolving around our x-axis. So we actually want to leave things here. You can use your calculator to help you graph these, but you can also use what you know about transformations. This is a square root of x graph moved which direction? Up 1, right? And a parabola moved up 1, but we're revolving around y equals -1. So putting all of that into our picture here, the same functions we saw on the last page, that square root of x but moved up 1, our x squared moved up 1. So we get that same little picture there, but our axis of revolution is down here at y equals -1. So that's what we're going to revolve around. So if I think about reflecting that picture over, so we'd be down here. And our area up here gets revolved around that axis. Our washer connects our outer functions, circling that axis of revolution, and our inner functions, circling that axis of revolution. And it's really the length of the radius is the conversation we need to have on this one. Okay. So again, as we zero in on just one washer, okay. First of all, this center of our circle is down at -1, and our outer function was this curve right here, which is your y equals the square root of x plus 1, right? So as we talk about our outer radius, top minus bottom always. So the difference between our function and our axis of rotation would be x square root of x plus 1 minus -1. There is your top minus bottom, right? We all okay with that? I know these get a little ugly here, so I'm going to clean that up because 1 plus -1, or 1 minus -1, I should say, would be x square root of x plus 2. No, because the y-axis and the lines y equals something are actually not the same direction. So we are revolving around a horizontal line, which makes it very similar to revolving around a x-axis. Does that make sense? So it's actually kind of like x-axis and y equals lines are the same process, and the y-axis and x equals lines would be the same, because if I went back to these, I actually could swap out the word y-axis with x equals 0. Does that make sense? So equivalent to, and the x-axis is equivalent to the line y equals 0. So all y equals lines are horizontal, and we have a very similar approach to it. Okay, so we need to finish up our inner radius here. Same idea on our inner radius. Your inner function is that x squared plus 1, this guy right here, to our axis, so top minus bottom would be x squared plus 1 minus the bottom, which is -1, which is x squared plus 2. And your area gets a little bit just ugly on this, and I wouldn't worry about cleaning it up at all. Our big radius, square root of x plus 2 squared, minus our small radius, x squared plus 2 squared. And all of that is going to go inside our integral. We actually already looked at where those intersect. It's still over at 1. It would be a 1, 2 this time. But we are still integrating along our x-axis from 0 to the edge of that intersection, which would be over at 1. So volume with respect to x, stacking up along our x-axis, will go from 0 to 1 of that entire area equation. Also a little cumbersome to write in your calculator, so let's make sure we're good to go here. Yeah.
I just did now, but so when we wrote this one, it was like what was in the parentheses. We didn't have that squared there, or was the square?
No, you need to square each one individually.
Okay, so I can't.
Big R, no.
Okay.
Nope. Big R squared minus little r squared, not the quantity squared.
Okay.
Yep. Okay, this one is tough to type in your calculator. So let's get, I'm seeing 5.131 on several calculators here. 5.131.
I still don't know if should I do that? Because I've been sleeping on
You don't have to. This one ends up ugly anyway, so I don't think we really leave it in terms of pi. But you can. That's fine. You can always say the pi till the end. And just take your answer times pi. 5.131. Questions? Okay, we got one left for us today. All you need to fill in on your note sheet is that we are integrating with, or sorry, revolving around the axis x equals -2. Both. I mean, like the last one would obviously be a calculator question, but if they are pretty tame and easy to do an antiderivative of, it's not out of the realm of being able to be. So one of the things you'll notice, I had a question as you guys are getting this one drawn and deciding which direction you're integrating and all of that and how you need your equations. One of the things I want to say to you guys is that it is very common for this to be a calculator question, or not, sorry, a non-calculator question, but at the end of it, a lot of times it'll do something like you saw in that one worksheet where it'll say set up, but don't evaluate an integral, because sometimes if we like switch our direction of integration or whatever, it can get to be a very ugly antiderivative. And so they recognize that. They're not going to ask you to do something ridiculous, but you may end up having to like set up an integral, but not have to solve. Okay. So are we integrating with respect to X or with respect to Y this time? Y. Our axis of revolution is a vertical line. And so that means our washers are going to be stacking up from bottom to top as we revolve around that vertical line. So let me catch up to you guys and get a picture of this, which is nice because that means I don't have to change my equations, right? I want them to say X equals something in terms of Y. If I'm going to revolve around this line, X equals -2. Okay. So let's see. Can we talk about, I don't know how to graph this necessarily, okay? So although we do have them in the format we want them in, if I need to go to my calculator to get help on graphing these pictures, I might want to say, okay, well, what would this have been as Y equals? And because your calculator has Y equals, right, as we graph them. So I may want to think about, I know how to graph this. That's the line Y equals X. But this one right here, it's a little misleading because your transformations do not work the same in terms of Y as they do in terms of X, okay? So if I were to just solve this for Y real quick so I can see what this graph looks like. Okay, go to your calculators. Graph that for me real quick. The only reason I say go to your calculators is we might be a little bit tricky on the whole -x+2 thing with our transformations. Actually, it moves probably opposite of the direction you think it should. It's reflected over your y-axis and then actually moved right 2 instead of left 2. We didn't, the way it's written. So let your calculators help you on this. Any questions for me? All right, so we have this part here, but we also have this part here bounded. Ooh, let me get rid of that for just a second here. Do this in a couple colors here. It did not say in the first quadrant, right? So as we look at this, we really do need to draw the whole thing. This region right here then is what is getting revolved around x equals -2. Say your question again.
So like the x equals -2, that
Why wouldn't it be here? The area itself is what is bounded by these two graphs, not the axis we're revolving around. So this does not bound our region. This is just telling us the region bounded by these graphs. And that shaded region is then what we're revolving, okay? Now, again, I need to know their points of intersection to know, first of all, are we all the way to my axis? Where am I starting and stopping my integration? Yeah?
is that flat line you have, is that like a 0 or is that your -2 line?
I have not drawn x equals -2 in there yet. No, I have not drawn my axis of revolution because I was going to look at our points of intersection just so I can draw this semi-accurately here before I get that in there. So if we look at how these intersect, let's see, we can do some substitution. And our 2 points of intersection are going to be at y equals -2 and y equals 1. And putting those back in here, I know that when I sub those back in, it is on the line x equals y, so that it'll be the same points. So 1, 1 would be here. That's one of our points of intersection. And -2, -2 would describe that point of intersection. Still good. Okay, why did I do that? Because I wanted to know exactly where to draw my axis of revolution. So our x equals -2 is actually going to go through that point right there. Here's the line x equals -2, and that is what we are revolving around. Okay, so again, if I consider flipping this shaded region over that line, we would get, let's see if I can, this picture here where my washer will be connecting again my outer function circling that axis of revolution, and my open hole will connect those middle lines. I know I solved this for y, but we are going to go back to our in terms of x because our washers are going to stack up from bottom to top on this. So we do want them to say y equations in terms of y as I identify the radius, which is going to go from our axis here out to the edge of our circles. So our bigger radius, when we are integrating with respect to y, our washers are laying horizontally, needs to be right function minus left function, especially if our axis of revolution is not an x or y axis, 0. So our right function here would be our curve -y² plus 2. Minus our left side of that radius is the axis, the line x equals -2, which gives us a radius of -y² plus 4. Questions? Smaller radius, again, right, which is our line x equals y, minus left, which is our line x equals -2. So it'd be right function is y minus left function is -2, or y plus 2. So then our area, and again, I would leave this just as is and not deal with cleaning it up. Big radius squared minus small radius squared. Big radius being -y squared plus 4 minus small radius y plus 2 quantity squared. And finally, going to our volume formula. Our volume formula, again, remember we are integrating with respect to y this time because our washers are stacking up bottom to top in that picture along a vertical axis of rotation. Means as I set my bounds, I want to consider what the y value is for my areas. Lowest that area is at -2 up to 1. So sometimes, as you guys are getting this typed in your calculator, sometimes they do nicely give us the equation in the correct format that we needed it. You may need to consider what it is as y equals so that you can use your calculators to help you visualize what that picture looks like. Because again, transformations are really opposite of what we think they should be when it is in terms of y. All right, so I am looking for a table who agrees on an answer. What'd you guys get? And I saw some in decimals. Is that the same as our decimals? 67.858, you said? Questions for me? Okay. Congratulations on learning everything calculus. We made it. Okay. All right. Your last assignment here. Again, guys, help yourself out. Draw those things. Follow kind of our little bit by little bit steps as I do them in the notes. It really does help break down like an overwhelming problem into like small achievable chunks. 1 second.